questions.
All right. Okay. So we'll go ahead and do that then. So you're being recorded as we speak, I believe. Yep, we are being recorded. So this is more of a question and answer anyway. So, okay. So now that I think everybody who's going to join us is hopefully here, and hopefully as they join, they can catch up. So the goal for today is basically to answer any questions you have. Make sure we are all comfortable with how interrupts work, because you're going to do a lab, and then you definitely going to have a big question in the exam about interrupts. I guarantee that. It's going to be very similar to your quiz, but it's going to be there. So I want to make sure you guys are comfortable with that. Then I want to make sure we have enough time to go through every section of the book and kind of highlight some of the key ideas you need to be good with, because that's the which that is going to show up in the test, and those are the things we want you to take away from this course. Okay.
So Azad, real quick about that test that's coming up on Tuesday. Can we use notes? Can we use the sheets, like the
summary sheet? Yeah.
Yes, the summary sheets and things like that. Like, are we allowed to use those tools on our test?
Yep. You can use. It's an open book, open notes. So if your notes and books are electronic, then you get to use them electronically. The only thing not allowed is asking somebody a question and then doing it. All the passive things are okay for you to use.
Okay, sweet. Because I know we're going to be on camera, so I just wanted to make sure.
Well, you're all set. You guys are all set. So this is exactly how you're going to take the test.
Okay, cool, awesome. I just wanted to double check on that.
Yeah,
thank you.
You're gonna join, and then on Canvas you're gonna click and go through it. Pretty straightforward. Okay, very good. So I think while the rest, if you have questions, go ahead and put them on the chat, and I'll get to them as soon as I can. But right now we have two questions that are outstanding. Both of them are about lab 4. Is it 4? Yeah, lab 4. And I want to emphasize a few things as we are going through this, and I want to make sure you remember what those are. One is this whole business of priority, and how do you distinguish the priority? So we have 3 interrupts, right? We have interrupt 0, we have interrupt 1, and we have interrupt 2. Okay? If you set an interrupt to a high priority, it is gonna jump to where? It's gonna jump to location 8. I'm sorry, yeah, 8. If you set it to low priority, it's gonna go to 1.8. And these are all hex values I'm talking about. So when an interrupt happens, you will jump and start executing this if it's high priority. So this is important for you to remember. So high priority, location 8. Low priority, location 1.8. Okay. Now, the question that came up, and in this one kind of shows you how you do it. Now, you don't have to memorize this. Anytime you want it, you just go here and look it up. Okay. How to initialize interrupts and do all of that stuff. I'm not going to too much worry about you memorizing this. Just there. Just go use it. Okay. Very little ever changes there. What I would like you to know is that when you have an interrupt, these two are imperative for you to do if you want to get another interrupt. You got to clear the flag, and you got to do return from interrupt. This is very, very important for you to do. Does that make sense?
Professor, do you mean to be sharing screens right now?
Yes, I am. Thank you. Nobody was asking. Thanks, Said.
I assumed you were just making comments.
Yeah, well, yeah. But let's see. I don't know what I'm sharing now. I thought I was sharing something, but it didn't decide to share. Oh yeah, you guys are seeing something, right?
Yeah, we're seeing the lab sheet.
Okay. So what I was last talking, and thanks again for letting me know. So these two lines, whenever an interrupt happens, you gotta remember to clear the flag and return from interrupt. If you don't do those things at the end of your interrupt service, you will never ever get an interrupt again. These are the cleanups you have to have. Okay, so remember that when you're doing the exam. Remember that when you're doing the lab, because those would be a requirement you have to have. Okay. So hopefully you've had a chance to look through this thing. This code basically comes through, said, okay, if you gotta, when your machine starts from a hard reset, power on, you're gonna jump and execute whatever it's in main. Whenever high priority happens, you're gonna jump to HPRO and do that stuff. Whenever low priority happens here. And this happened to conveniently have one high priority and one low priority. So Tyler had a question, he says, wait a minute. When I'm doing this lab, this actually have 3 interrupts. You see that? So I've got a, so I'm gonna do it on like this better than the one that comes with the computer. So he says, okay, so I've got on my main, which whenever I power up the machine, I jump over there. And that thing, whenever I power up the machine, I jump to location 0x00. This is the reset vector, okay? And what do? I sit there and every 10 seconds, the main part of the code toggles every 10 seconds until, okay. So you sit here and you do a bed toggle of port B, comma 7, fair enough? You just sit there and loop and do that and maybe put a delay in there so you do some delaying and whatever. So that's that. Then it says whenever interrupt 0 happen. Now what is interrupt 0? When an interrupt 0 happen, where do you go? Which location?
08, the high priority.
08, exactly. So you're gonna, because this is high priority, you're gonna jump to whatever is in location 08 or 8, right? And that's where you are. So now that's great. How about interrupt 1? Where do you go in interrupt 1 when interrupt 1 happens?
You're still going to go to 08.
Yeah, so since that is also set to high priority interrupt, you're going to end up in the same exact location. Now, the last one is interrupt 2. When interrupt 2 happens, what do? Interrupt 2 happens is a low priority, which means you go to where does low priority go?
That one's going to go to 18.
1.8, yeah.
Can I ask you a quick question?
Go for it.
So you already had mentioned the test bit for int 0.
Yeah.
Are we, or should we test for int 1 also? And make sure.
Depends on how paranoid are you. Yes, how paranoid you are and how good a code you want to write. And are you going to cross your finger and everything is going to go perfectly right and you're never going to have a problem? But what do I mean by that? So if you test for int 0 and it's not 1, then you can assume it's int 1, but you're assuming, right?
Mm-hmm.
It could be some other crazy thing that is causing an interrupt that you didn't know about. So if you want to be very precise, you check for interrupt 1, but for this class, you can get away with not checking. But the reason I bring that up is this is kind of defensive programming, or kind of get it done quickly and be done with it type of things, which usually bites us in the end anyway. These are how bugs and security issues get into.
So let me ask you this then.
Sure.
So anytime it goes to 08, is it going to toggle RB5 then?
No,
so
because look at the lab requirement. Look at the lab requirement. What does the lab requirement says? The lab requirement says when it's int 0, you said RB6. When it's int 1, you said RB5.
So we should test for int 1 then.
You have to test. You have to, at least the minimum you have to test if it's int 0. So you could. So what you do is basically when you. So this comes to location 8, you send it to this thing called high priority interrupt, right? Code. And then you say, okay, is you're going to check to see. So you're going to do a bet test F skip either way. So let's say skip if clear, okay? And then you're going to say, okay, what am I going to test? I'm going to test, oh, I don't remember where, I'm going to test interrupt 0 flag. I don't know where that is. So we got to go look at it. Where is it? Well, a couple of ways. You can go to the lab. The lab itself actually tells you where it is, or you can go look into your trusty list of a special function register on the last 2 pages, and the last 2 pages kind of show you all the content, every bed in there. So all you have to, this is a little tedious, but you can see, if you look at it, you see that there is a register called int con, and in int con, the bet name is int 0 interrupt flag. You see that? So if that happens, I know that int 0 label, or whatever you want to call it, I know int 0 has happened. Do you see that? And then if not, okay, so at this point I could assume int 1 low is happening, okay? And we'll do it this way. Or you can do another bet test on interrupt 1 and say, is that the case? And if it is, do it. If it's not, say, hey, I don't know who caused the interrupt. I'm not going to mess with it, and I'm going to move on. But since in this case only interrupt 0 and 1, you can get away with just saying, okay, if I reach this point, then it must be an interrupt 1 happening. So if an interrupt 1 happens, then I'll go and do bet toggle something, port B, I think. Is it port B? And it's 5, right? And did you see how I didn't have to say which bet? I just put the name of the bet, because in that include file, they have all that's defined for you. You don't have to worry about it. And this is a preference way to do it, because if you go to a different processor that has the same setup but different locations, you can just use the code over again. Any questions on what I'm saying? Because I'm going through that rather quickly, so I want to make sure we are all on the same page. So now I'm going to jump here and do this. Then remember, what do I have to, what are the 2 things? What are the 2 things I have to do always before I return? I have to basically say, okay, I have to say clear
interrupts, and then you got a rectify.
Yep, you got it. So what is the best way to do it? I think the best way potentially is bet, use the bet clear F, and then say int con, and I don't know where it is. Where is it? Do you guys know? Oh yeah, okay. It is in int con 3. Everybody knows where I'm looking these up? Int con 3, interrupt 1 flag. So I'm going to clear the flag, and what was it? Return from interrupt enable, and I'm done. I'm gone. I'm back to whatever I was doing when the interrupt happened. You see how these are 3 distinct programs? Really, they don't jump into each other at all. It just interrupt really takes you away and brings you back. And then int 0 is over here. In 0 label, so whenever this was set, I would jump here, and I more or less do the same thing. Bet toggle port B, comma 6, bet clear F, int con 3, comma int 0. Oh, it's not 3. This one is in con. Clear the flag, return from interrupt, and you're done.
Professor.
And just because I did the testing on interrupt 0 first, that makes interrupt 0 a little higher priority. They're both high priority, but the first one to get service is interrupt 0, just simply because I am testing it first. So this is called the software priority. You see that? Through my writing of my code, I have given interrupt 0 a higher priority than interrupt 1, even though both are high priority. Does that make sense?
So real quick, Azad, in my lab when I did that, just because of the way that I wrote it, I gave interrupt 1, like I did what you did, but I did interrupt 1 and tested for that first, and then it went to interrupt 0.
This is
Should
fine.
I-
Perfectly fine.
Okay, so
Because it's not very clear. That is not a requirement of this code to say.
okay, all right.
To say this is higher than that. I suppose that would be an improvement on this lab to say, set it up. Don't even tell you how to do it. Set it up such that you have, let's say, 3 interrupts and they're all high priority, and let you figure out how you're going to do it. But and then say, okay, interrupt 0 would be the highest priority, interrupt 1 would be the next priority, interrupt 0 would be the. But that's not what this lab is about. This lab really does not make a distinction between which one is higher priority, 1 or 0. That puts about the same.
Okay, sweet. I just wanted to check, make sure that, yeah.
Good question. Good question.
Professor, I have a question.
Sure.
So, for when the interrupts are executed, it takes us to PC08, right?
When the high priority, so let's say there is a pin on the chip, right? The pin on the chip is called int0, let's say, and you give it a pulse. So you go to the stimuli, right? You go to your stimuli window, and you put a int0 in here, right? And you say, okay, the action, I usually like toggle, but you can set it to go. So you hit it, goes from 0 to 1, right? And then you get an interrupt. Go ahead, now yours. So yes, at that point, you're in location 08, yes.
Right. So the way that you programmed it, you used the labels
Yes,
in 0. So are those reserved to always point to 08, or?
yes, those are always go to 08.
Okay.
Now,
Okay.
now I want to make sure I'm not misdirecting you. So I want to make sure we go back here and just do a little more explanation on this one. So when a high priority interrupt happens, it always, and this is saying put this code, this is saying put this code at location 08, right? That's all it says.
Oh, I see. Okay.
So
Okay.
it always jump to location 08. Once it gets there, it finds the go-to. What does the go-to do? Go-to say jump over here.
Yeah. Okay.
And that, now your question may be, why just not write the code right here? Why do you do a go-to? Because I'm worried that if I put the code here, initially maybe is not 16 byte and it won't reach this point.
Yeah.
But later on, I add a few more code. All of a sudden, my code stopped working, and I wonder why. Because what has happened by adding those few lines of code, I've reached over here and overridden it. If I jump outside of these special locations, that chance doesn't exist. So this is a very common practice when we write low-level codes like BIOS and operating systems and systems.
Okay. And that's exactly the code org. I've never seen org before, so that's the code that we need to set.
You
that
have seen
location
org
to-
because you've always have had org 0.
Aha. Okay.
Or
Okay.
zero. The
Oh, I see.
reason you might not paid attention to, which makes sense because it was always there and never really mattered what it did. So what an org does, org is not an assembly code. It doesn't have, when I go to the disassembly code for this, it doesn't show up as anything. All it does, it says this location starts at location 0. That's all it says. So let me kind of put it in practice. Let's go back here. I think we have, yeah, we have the disassembly code. Oh, don't. Or maybe I have to assemble it. Let me see if I can assemble it. All right. I was going to show you. We go in there and mess with it, and you can kind of see what happens. So loading. Oh, I have the load set. I'm getting sidetracked. I'm wondering why my disassembly code doesn't show up. So debugging, output, disassembly listing, oh, there it is. See how, see this org here? See, there's no assembly code associated. And notice the label doesn't have assembly code associated with it. The first line of code is here. And that first line of code is put into location 0, 0. You see that?
Yeah.
Now, if I went back to the code again and changed this location to 8, right? It's going to move, it's going to start that code at location 8. It's going to put the very first piece of code in location 8. Let's see if it does it. And there it is. See that?
Yeah, makes sense.
This was a good question because that's another confusion that people get into. Like sometime I give you a piece of code in the test or to quiz or whatever and say, okay, tell me which address it starts. So when the org is sitting here, org itself doesn't start on location 8. The very first instruction starts on location 8. I better change that to 0 or else then I'm going to wonder why doesn't this work when next time I'm doing demoing this thing. What happened? Oh. Okay. All right. Okay. Let's go back. Let's see. Well, there was another. I think we covered everything, right? Tyler, right? Did we miss?
I think so. Yeah, I think we got most of the questions I had on the lab.
Okay.
It was mainly just what is the point, and I wasn't understanding. I totally get it now.
And I just want to double emphasize again that before you return, make sure you clear the interrupt and make sure you return from interrupt. Those are really critical. And remember, high priority goes to location 8, low priority goes to location 1.8. And we only have 2 priorities for that space. And then Tim has a really good summary of everything we've talked about in the chat if you want to look at it. High priority is 08, low priority is 1.8. Gotta keep 00 to 020 clean for more cleanliness of programming and lowering our risk of funny things happening than absolute requirement.
So the other thing too, real quick. So for the low priority, we have to change the bit clear to interrupt 2 flag.
Yes, absolutely.
Right?
Yep.
Yeah. So we're gonna have to move some of that stuff around just to get this to. Okay.
There's a little bit of work in this lab. That's
Yeah.
And
Well, I was looking at it and
go ahead. Oh, did we lose you, Tyler? Oh, we might have lost him.
hope not. Do you hear me?
Oh, yeah, I can hear you. It might have been me who got lost.
A little glitch. No, what we were talking about it the first time, I saw that, obviously there's 0 and 1, and then I didn't really have any questions. I really started reading through it on Tuesday and realized there's no 2, and that just totally lost me.
Okay.
And so we clarified it though. We're good.
Yeah. So when you're up here, you let me just make sure for other folks who haven't had a chance to look at it. So what Tyler is pointing out is basically that in this code we are not using interrupt 2, which means when you get this far, you have to do this. You have to have another BCF int con 3 comma int interrupt flag in interrupt 2 interrupt flag. So you have to clear that flag just to make sure it's clear. And then up here, you also have to add another thing which does for the same thing as interrupt 1, does it for interrupt 2, enables it, okay? And then there's one more thing you got to do, and then you got to set the priority. This priority's got to be high, so this has got to be setf, and then BCF for interrupt 2 interrupt priority. So you got to do some changes at this level as well, okay? Is that too cursory, or did you have any questions?
So we just have to basically set that one. I missed that one. I was mainly talking about the low priority code down the bottom, but so we do still have to initialize it too then, and then clear it.
Yeah, basically it's a good idea to clear all the flags to make sure nobody's messed with you before you got this far. It's also, you are required to set the priority for interrupt 2 to low, so you got to clear that bit, and you got to enable interrupt 2 by setting the corresponding.
Gotcha. Okay, that makes sense. I'm glad you touched on that because I probably would have missed that and that would have caused some issues. I didn't
Yeah,
think
you
about
just
that.
wouldn't have got the interrupts, or you got some funny interrupts.
Yeah,
And
you
then-
would have received an email later with a question going, it's not working. What's going on?
And then I wanted to make sure we covered the question you had in the beginning of this lab, with this conversation, which was how do you cause the interrupt, and the way you do that
Yeah,
with stimuli, and there's int0, int1, and int2, and by toggling them you cause it. And the way it's set up, the code is set up right now, only on the rising edge you get the interrupt. So sometimes you have to toggle twice before you get the interrupt.
Just to clarify for testing, should we have it just running and then trigger the interrupt, or should we pause it and then trigger the interrupt and step through a couple?
I have found this thing not to work if it's running and you hit the semi-stable. I don't know what other people's experience is. So I would put a breakpoint someplace and
Okay.
then hit the interrupt and then continue to see if the interrupt takes place. Okay.
So maybe put it in the interrupt and then hit the, okay.
The way I would do it is, if I was doing it to test this thing, what I would do, I would put a breakpoint right at main, right? And I
Mhm.
would put a breakpoint right at the high priority. You can't put it on the label, but write the first instruction high priority, and another breakpoint at low priority.
Okay, that way if it does get
Alright.
triggered and goes into there, it stops and shows you.
And you
Gotcha.
don't have to sit there and hit single step to figure out what's going on. You just continue. And if it
Yeah.
doesn't go there, maybe click the interrupt one more time or two more times to catch it. Because it's a software simulation of piece of hardware, sometimes it misses your interrupts if it's not watching it close enough. These are event-driven applications, so.
Yeah, I noticed that you can't see the variables in real time. It's only when you pause it or stop it, it'll show you.
Okay, are there any other question on interrupts, on Lab4, or anything relating to that before we transition to what's going to be on the test and kind of walking through that?
I don't have any more questions for the class, but I do after class if you have time or you have
Absolutely. I have an hour after the class, and I was wondering if anybody thinks it's worthwhile if I show up like a half an hour before the class starts on Tuesday. So if you have any remaining questions, would anybody be interested in attending if there was like a half an hour you guys could ask questions before the exam?
Yeah,
Okay, I'll make
Yep.
sure. I'll make
Yeah.
sure. I'll make sure I'm there. Okay. I better write it down because actually, you know. So 9:30, at least 9:30. I might be there even earlier, 9:30 on Tuesday. Okay, cool. So let's go ahead and put this away. And let's go ahead and go and see what's going to be on the test. So I keep saying this, and it's honestly true, is that I literally get my questions for the exam right out of your quizzes and homework quizzes, okay? And I change a few things just to make it a little more interesting. But literally the questions come out of it, and I try to stay relatively true to the way those questions are being asked. Okay, so I would say the best preparation is to not even old tests, because they will change. Just look at the quizzes and make sure you can answer the questions without looking at the answers. Okay, and if you could do that, then you're in good shape. Okay. That means homework quizzes and just regular quizzes. Then you will be in perfect shape. And time is not tight, but there's not a lot of time to do research during the class time either. So if you got to do research and learn the material during the test, you'll run out of time. But if you already know it and you got to look up a few things, that's just fine. That's included in the test. All right, so let's start with chapter 1. Chapter 1 was very high level stuff. So what were some of the key things in there? Well, some of the key things we talked about there was like, okay, when you write a high-level program, what happens to it? Well, it's going to be compiled, assembled, linked, and all of those things. So you got to remember what those are. What is a CMOS? Who cares? Why? What is a Moore's law? What are the design considerations? What's important? What's not important? Is memory more important? What's the difference? You know, if I'm going to buy a computer, what is the first thing I look at? Is performance, maybe form factor, cost, price, things like that. So that's stuff. So there was a bit of things about, you know, what is a microcontroller versus what's a microprocessor? What's the difference between them? You still got to know those things. That was pretty much it. And PICmicro, which processor we are using is a PICmicro 18F1220. It's from Microchip. It's a RISC-based. So the question would be RISC versus CISC, some of that stuff. And it's usually going to be, here are some statements, which one are true, which one are false, or whatever. Drop down many questions. Let's see. So that was chapter 1. Chapter 1 was really kind of fuzzy, if you will. And most of the question would be kind of tell me what this thing is, or tell me what that is, definitional questions. Chapter 2 is where the meat of it is going to come from. And I want to spend a little bit of time going through this. So what are you going to see here? One of the things you're going to see in here is going to be, do you understand that these different kind of operations? We have, you know, we spend a fair amount of time talking about byte-oriented, bit-oriented, literal-oriented, and control operation. There's a memory block move, so there are 5 types of instruction, but we really didn't spend a whole lot of time on the 5th one. But if somebody asks you how many types of instruction is it, don't forget it is 5. But in here, so byte-oriented works on bytes, literal bit-oriented works on bits, and then literal brings constant in and takes constants out of registers. Control operations are the branch, the call, and all that stuff, go to, and all of that stuff. So in my past experiences is usually what I would do. So one of the questions would be, okay, here is an assembly code. For example, here is the AND WF 0x80, 1. Translate, okay, so what is the machine code? And the machine code is always asked in hexadecimal format. So I've never, most students don't have any problem making the translation this way or this way. Sometime I will give you the machine code for this and ask you to give me the assembly code. And typically, I think 90% of you will get that right, and 10% who don't get it right is just a, you know, some transposition of numbers or something like that. Everybody seems to get a pretty good grasp on that. Where things fall apart, and that's what I want you to spend some time doing, is for this particular instruction. So for these guys, no problem. You can translate, I got confidence in you. For these, it gets, so the branch especially, and then the call and go to, which are very similar, have a problem when I'm asking you to do a machine code or go back, okay? Because when you're doing branch, the end value has to be calculated using PC new equal to PC branch plus 2 plus 2n. And n is in 2's complement. So you always got to use that equation, because what you're trying to calculate is the relative distance from where you are to where you want to jump. If you're jumping back, it's going to be negative. If you're jumping forward, it's going to be positive, okay? So that's the critical stuff there. GoTo, on the other hand, has the whole PC except for this least significant bit in there, which least significant bit is always 0. So the way you do that, you add a 0 or you take a 0 away, depending on which way you're going, okay? So let me stop right here. So that you're going to have at least a handful of questions asking you, here is a assembly instruction, tell me what the machine code is, or say, here is And here is my assembly machine code. Tell me what assembly codes I have, and then there's going to be one or two about the branch. You know, give you a piece of code and say, okay, here's a piece of code, and tell me what's happening, and what is the machine code for the branch. Okay, and that's it. Now, one other thing is pay attention. Sometimes I give you an address of the first instruction, then you gotta calculate the instruction for the rest of them. So pay attention that some instruction, for example, move FF is 4 bytes, not 2 bytes. So you gotta go from where you are +4 to get after it, okay? By the way, I'm running through this rather quickly. If I say something that doesn't ring true or is concerning to you, bring it up, bring it up. Let's see what else can we do here. Oh, and then there's going to be one case where I'll just give you a little piece of code and ask you to make some sort of a determination about what it's doing. So what you need to do, I don't know, some could be something like this: move W, LW, maybe 25, and then let's say increment or decrement W register, and then branch 0, branch not 0 to loop. Okay, and loop is maybe loop is down here. And then I'll ask you, what is the value of Z, status register, status bit Z, if my execution is here? If I've reached after the branch, I'm executing the code right here. My question is, what is the value of Z? Actually, I would like you guys to think about it and see if you can respond to me, and you can respond directly to give everybody a chance to think independently. And let's see if I can clean this up a bit. I'm going to write it over here. So we've got a move. Could be about a carry, could be about the brand 0, whatever it could be, but it's something like this. Move LW 25, decrement, oops, loop. I'm rewriting it so it's easier to read. So you're executing the code that is right here, right after the branch. And my question is, when you get over here, what is the value of C?
So you're not asking what's the value of W register, you're asking status bit.
Status bit. Mm-hmm. So you got to think about what condition gets you to that point. What has to happen before branch dot 0, before you get to there.
Oh. That was a trick question.
It's not meant to be trick, but they do happen to look tricky because you think of 0 as being 0, right? But the 0 flag is saying that Z is equal to 1, says the result of your last operation was 0. So I got a couple of answers. They're both correct. I like to hear from a few more people, or let me know if you're wondering what the heck am I asking about as well. I'll be happy to work through that.
See, that one, for whatever reason, I thought we were just, obviously decrementing the one time, and then, what is the status bit Z, but I guess it would go through that loop.
Yeah, as long as this operation, decrement W register, as long as that operation, the W register is not 0, then this will jump back to the loop. As soon as it becomes 0, it jumps here. So when it's 0, Z is equal to 1. So you are all the people who answered, you're absolutely right. So Z has to be equal to 1 before we get. If you are struggling with this, this is really important stuff. You're going to see these in the quiz. Okay. Okay. All right, so that was chapter, that's the essence of chapter 2. There are some memory questions. It's good for you to know that we have the separate program memory from data memory. And we have 4K of data memory. We have, no, I'm sorry, we have 256 bytes of data memory, and we have 4K of program memory built into this chip. So these are kind of good things for you to know. There may or may not be any questions on this one. This is kind of a lower, it's good for you to know, but it's a lower priority. This whole business I talked about earlier is much more important for you to have an understanding. Input and output. So this one really gets at your understanding of port A, port B, Trish A, Trish B. So questions, sometimes you gotta have a good handle on it, because sometimes the questions could be a little tricky. So I want to make sure you're good with it. So let's say I might be like things like this. It says, okay, move. You might get a little code. It says move 0x, let's say 1f. Okay, and we're gonna move this thing to Trish B. Okay, and then it says, okay, move LW. Okay, move LW. Let's say 25 into W register. Then it says, okay, move WF, move the 25 into port B. Okay, and then it says, okay, so we know that Trish B bits (0 through 8) basically say whether our input or output. So this is going to be input. This is going to be input because of the F. And this is going to be input. This guy is going to be out. Any question of how did I get this? That's 1F. I turned it into binary. O output, 1 input. That means that this data is going to come in from the pin, right? To the processor. This stuff is going to go from port B out. And then here we say, okay, what is port B is set to? So port B is set to, so I'm going to line them up so you know which one is which. So now it asks you, is port 0 through 8? So ask you choose the values in location. So the first thing is, it says, okay, choose from these values for each bit. Question mark, I don't know what's in there. 0 is in there, 1 is in there. So based on the information given to you, what is in bit 0? Let's try that. What's in bit 0?
It's going to be a 1.
All right. So we have a 1. We have a proposal for 1. Anybody wants to disagree with that? So I'm assuming the 1 comes from the fact of 0. We have someone who says 0. Okay. So how about question mark? Anybody wants to go for a question mark? Okay. So I think if you look at
hold on. So we're moving 25 into port B, is what you're saying.
Oh, bit 0 is question mark. Okay, this is beautiful. We've got one of everything. We've got a 1, we've got a 0, and we've got a question mark. Now the question is which is right. So let's walk through it. So the first thinking is, hey, you're putting 25 into port B, so you're putting a 1. 25 is 1 0 1 0 0 1 0 0. So you say, oh, that's obvious. That's a 1. But look what this is set up to. This is set up to see what is on pin for RB1 and puts it in. So since nobody told you what is on RB1, the correct answer is I don't know. You see that? And that same thing is true for all the pins that are set for input.
So real quick, even if you move something to a port, right? If you move those 2 bytes to that port, right? If they're an input, then you still can't read from that because it's an input,
Well, you're
right?
reading it, but you're reading what is on the external port. If it's a 5 volt, you get a 1. If it's a 0 volt, you get a 0.
Right. So regardless of the code before that, even if, so, I mean, it's almost like you can't even really move actual like literal numbers to an input port, right? It has to be an external.
It basically ignores it.
Gotcha.
That door is closed. They have doors. They basically, when you say the input, it closes the door to the processor's right. It opens the door to what input is coming from the pin. And when you say
Okay,
it's output, it does the opposite. And then of course the last 3 bits you can say 0 0. Oh, I'm sorry, 0 0 1.
Yeah, I was gonna say those are outputs, right? So
Yep, 0 0 1. So you're going to see something like this, some variation of this in the test as well. And I think you had a variation of this in the quiz and other places as well. And then so we move into chapter 4, and chapter 4 really the first big thing was the first big thing in chapter 4 was stacks. Okay, so the things you want to know is stack pointer is a register, right? Is a register in special function register. Its name is full name is stack pointer PTR. It's got like 8 bits in it, and I gotta look at it. Oh, actually, I guess. So we're gonna go to the stack pointer on my little trusty sheet, and the hardest part is finding it. It's right on the first page of our listing, and so the first 2 bits say if it's they're set if it's full or empty. So this one is empty. This is full. And then this bit, the next bit is always 0, and these 5 bits from 0 to 4 are which the top of stack is pointing at. So let's start. So for example, if this is the stack, if you just starting fresh, then it would basically say my stack is empty, and I'm in empty location 0. So you're gonna get a 4 0 put in the stack pointer. Okay. Now let's say you make a call. When you make a call or push or whatever, something goes in here. Let's say goes 0x920. Okay, goes in here. When that happens, then you have a 1 in here, and you are no longer empty, so these will be 0. So the next one is going to be 0 1. So you need to be able to do these things. Okay. And then you might be asked, okay, so this is the top of stack, which means the stack pointer is at 0x01. Then what is on top of stack upper, top of stack high, and top of stack lower? You say, okay, these 2 are in the lower section. This is in the higher section. And then on the upper is a still 0. The other thing that has, so call, put something on, return, pulls it off. Sometime I might ask you also, what is a push? So I might have an instruction say push, and this is in location 2-8. That's probably the trickiest of anything I can give you. So then it's going to ask what gets put on the top of the stack. So the top of the stack is here, now moves up here. And now the question is, what do I push in here? I push the next address. That's critical. So I want you to think about it and send me a message. Yeah, very good. Somebody's really fast already told what it is. And the reason I say this is tricky is we are always thinking decimal. So sometimes we forget that this is in hexadecimal. So you might say it's 30, and that would be wrong. If it was decimal, yes, 28 plus 2 is that. Sometimes also folks say it's 28. It's not 28. It's the address of the next instruction that gets stored. So yes, indeed, it's going to be 0x28. That is the correct answer. And the stack pointer now is 2. So you're going to have a few questions about stack, about calls, about pop, push, that kind of stuff. And usually asking what's the top of stack, what's bottom of the stack, what's when you're gonna. So let's say this is gonna be weird, but let's say my stack is set up exactly like this, and I do a return. I execute a return instruction. My stack looks like this, and I do a return instruction. The question is, what is PC? What is in the program counter as soon as return is executed?
Isn't it the original PC plus 4, right?
No, it's 2A, because 2A is at the top of the stack, right?
Oh, 2A, okay.
So the top of the stack gets pulled off, and that becomes the new PC. So
And it pops the top of the stack, right? Doesn't return pop the top of the stack after that too?
it removes it, yeah. So it removes it basically from the top of the stack, moves it down here. Now we are looking at 0, 0. So talk about messing yourself up. If somebody's done this in your code, trying to figure out what in the world is going on is next to impossible. And thank goodness you guys don't have to fight the logic analyzer. At that point, you look up logic analyzers and try to walk through the code one step at a time and see which address is going, which machine code is executing. Then you discover there's some idiot put a push in there. So push can really mess you up. We do use them for special purposes, but it better be a really, really good reason to use push and pop. Push and pop should not be used unless there is a extremely good reason for it to be used. And I don't know very many good reasons for it, because that's a way to confuse everything. Okay, so now we get into to these time interrupts. Interrupts, we've talked about planning. So you're going to probably, given it that this is kind of the easiest way I can do it. I'll give you a little piece of code, explain what it's supposed to do, and I leave some blanks in there, and you're supposed to tell me what goes in the blank from a list of items I give you. Does that make sense? So, for example, it says high priority is supposed to do that, and then might leave, where that instruction is, and then you have to put it in. Just like I think there's a quiz like that in one of the quizzes that you did, or you will do. Yeah, well, you probably do today. Okay, so the next question that comes up is really, and I want to spend a little bit of time on it. We talked about it when we were doing the delay, but I don't think I did a good job of covering it. This processor is able to change its clock speeds all over the place. So we once in a while have a need to understand how long does it take for a piece of code to execute, okay? And so I got to do some definitions. So oscillator stands for the clock, how speed the raw clock speed is. Our default, if we don't do anything, our default is 32 kilohertz, and kilo is 10 to the power of 3. But it could also be like, we could set it to 4 megahertz, 1 megahertz, 8 megahertz, whatever. Now, and notice these actually are what I gave you is the frequency. So frequency says how many times they go up and down in a second. The oscillator is TOC, so it would be 1 over. This is 1 over frequency. So the period it takes, how long it takes to get something done, is 1 over the frequency. So for this one, it'll be 1 over, basically would be 1 over 32 times 10 to the 3, which the way it gets translated, roughly ends up being 32 microseconds. Okay. And this one is going to be, basically, if you do it, it's going to be 1 over 4 times 10 to the minus 10 to the plus 6, which means this is going to be 0.25 microseconds. That's each oscillator. We don't care about that, but we do care about the oscillator because for us, we need 4 clock cycles to do 1 instruction. So there is this idea of a period for instruction. So when it's saying some instruction takes 1 cycle, it's saying it takes 1 instruction cycle because this size, not the oscillator. So this is basically 4 times the T of oscillator. So the instruction period for the instruction cycle period is equal to 4 times that. So for the default version is 120 microsecond. For this one I picked randomly 4 megahertz is 1 microsecond. And all we're doing is we're multiplying these by 4. Any questions so far? All right, so now somebody may give you a little piece of code which includes, I'm going to throw some weird stuff in there. It's going to do move FF port A and port B. It's going to do clear F, I don't know, 0x80. And then it's going to say delay, wait, decrement. Sure. But that's really not nice. Okay, let me just modify this slightly. That was more than slightly. Okay, so I'll set F0x80, move W, move FF, port A, comma, port B. And then loop decrement F0x80 branch not 0 loop. And then they'll ask you how many instruction cycles does it take for this to be executed? Then you go to your trusty sheet again for the instructions and you look at it. So we look at setf and we say, okay, number of cycles for setf is 1. Right? Where did I do that? Okay. So now your job is to tell me what is the number of instruction cycles for move FF. Anybody knows what the instruction cycles are for move FF?
I think it's just 1, right?
Yeah, so that was a good guess. That was a good guess, but actually you want to look it up if you're not sure. It's 2.
Oh, it is 2. Oh, because you're moving from one port to another and you have to have the
Well, the reasoning is kind of, you got to be careful because sometimes they don't follow reason. You just want to look it up.
Fair.
I mean, if you knew exactly how they're doing it internally, it would make sense. But sometimes when you're looking from the outside, it's kind of hard to tell what they're doing. And then decrement, you do the same thing. If you're ever in doubt, look it up. You're going to find out this is 1. And since we've done this before, I know this is 2 when it branches, right? And 1 when it doesn't branch. So this is it. So you say, okay, how many times is going to do this? Well, it's going to set it to F. If you set F, you set every bit to 1, so it's 255. So it's going to do 255 loops, right? So this thing is going to be done 255. except for the last time you have to subtract the 1 because the last branch doesn't take 2 cycles, it takes 1 cycle. So the answer basically would be 1 plus 2 plus 255 times 3 minus 1. So that's how long, if you say, that's the number of cycles, right? Number of instruction cycles it takes to execute it. If you want to know how long it takes, well, for the 1 megahertz clock, oscillator, you multiply it by 1 microfarad. I think it was 4. I'm sorry, 4 microsecond. So that's how long. For the internal one, which is 32 kilohertz, we multiply it by 128 microseconds. Because that's how long it takes for each one of these cases. That's how long it takes for each clock cycle to execute. So that brings us, that's pretty much it. We have not, so the test stopped right here. We have not covered anything beyond this point. So we have covered the interrupts and the oscillator is the last thing we covered. And again, if you do the labs and do a good job on the lab, you're going to get the interrupts pretty well figured out. And then if you look at the delay code, understand the delay code and do the timing on that, then you'll be in pretty good shape to do the times. Just remember that we can change the clock and then the oscillator changes and the instruction cycle is 4 times the oscillator. All right. Any last minute questions before we call it good? That's pretty much it. The test is